So what did we start talking about yesterday?
Related rate.
Related rate. So what did we say for us? What is a rate?
Derivative.
A derivative. So we're talking about derivatives that are kind of related to one another, but we also talked about how they are both then dependent upon time. First semester I gave you a handout for optimization that had a list of a bunch of different formulas on it. That might also be helpful for this section as well, because as with optimization, we're going to be looking at a lot of like geometric type things. So you will need to make sure that you know some of your formulas. But in general, a related rate is 2 or more. We will mostly stick to 2, but you could have more rates, or in other words, derivatives. That are changing dependent to another value. And like I said, most of the time what the rates are going to be changing according to is going to be time. So our steps. Our first step, we generally want to draw a picture. Again, we're dealing with a lot of geometric type things here. So just like with our optimization, how it can be helpful for us just to be able to refer back to a diagram, it's going to be helpful here as well. Next up, we're going to find an equation. That relates to that. So kind of within this, we need to decide like what those values are. So we need to decide what is given and what are unknowns, or like what they're asking for. Because depending on what they give us and what they want us to find, that's going to affect or determine which of our equations we want to use. So like yesterday when we were looking at volume and radius, we wanted to use the volume equation because V equals 4/3 pi r cubed has both volume and radius in it. We were able to relate the two together. Next, we take the derivative. But we are taking it with respect to time. And then lastly, we're going to take those givens that they gave us and plug them in so that we can solve for whatever it is that we're needing to solve for. Like I said, there's going to be givens that we're going to need to eventually plug in to help us solve for things. The key is that we can't plug those things in too early. Okay? Because again, we're talking about our derivatives being with respect to time, which means that when they give us, like, our radius is 4, they're saying at the particular moment when our radius is 4. I can't plug that in too early because if we do, right, we are not allowing the radius to change with respect to time. So we have to take our derivative first before we can plug in. Now, there will be some types of values, like if we have heights, like the height of a building, or the height of a person, something like that. Like, those aren't going to change, right? That's going to be, like, constant. So those you can plug in from the beginning, because it's something that's not changing. Are we all with me there? Alright. Questions so far on that? Ready to look at an example? Alright, we have our cone problem first. So it says water is draining from a conical tank. The height of the water level is changing at a rate of -0.2 feet per minute, and the radius is changing at a rate of -0.1 feet per minute. At what rate is the volume of the water changing when the radius is 1 foot and the height of the water is 2 feet? So what do we say our first step is?
Draw a picture.
Draw a picture. I have a picture, but you do not, so I would suggest drawing something similar to my picture. I included my radius of my circle. And the height of the water. So those are kind of the two things that the word problem is talking about. So once we have a picture, we need to decide on what is given and what we're looking to find. Because again, our goal is to make an equation, but we don't know what equation to use if we don't know what it is that we're looking for. So let's start with the first part. This says the height of the water is changing at a rate of -0.2 feet per minute. Why is it negative?
Because it's decreasing.
Because what's decreasing?
The height of the water.
Yeah, because it's like coming out, right? Which means my height is going down or decreasing. And remember that a derivative being negative means that we are decreasing. So how might I represent the rate the water is changing? So again, for us, what is a rate?
Derivative.
A derivative, okay. So I'm talking about the derivative of the height with respect to what?
Time.
Time. So how would I put that using symbolic notation?
dH over dt.
Yeah, dH dt. And they tell us that dH dt is
2 feet per minute.
negative point. Okay. What else do they give us? Okay, so how would you write that? And what is it that they ask us to find?
dV over dt.
Do they ask us just to find the volume? Because that would just be a geometry question, right? If I just wanted to find the volume.
When the radius is 1 foot and the height is 2.
Well, but it's not just the volume, it's what is the volume?
Oh.
Right.
The rate of the volume, right? Which would be
dV over dt.
dV dt. And then yes, they just give us that we want my volume, the rate of the volume, specifically when R is 1 and H is 2. Now my I going to plug in 1 and 2 from the beginning? No, because those two things are changing. If I just plugged into my volume formula with a 1 and a 2, again, that would be a geometry question. I'm just finding volume. I'm not finding the rate of the change of the volume. So speaking of, do we know what the volume of a cone formula is? No? Alright, one nice reminder. Volume, so V equals 1/3 pi r squared h. Does that relate the things that I'm looking for and what they give me? Volume, radius, and height.
Yes.
Yeah. Now, the nice thing about our related rates is that we can go ahead and take the derivative from there. So in a lot of ways, related rates are similar to like our optimizations. We have word problems, we have a lot of geometric type things, okay? We're gonna take the derivative. However, remember with our optimization, we only wanted to take the derivative of one variable, and so that's why we needed that like second equation so we could plug stuff back in. Here, because we're taking the derivative with respect to time, it does not matter how many variables we have over there on the right hand side. Are we all with me there? Okay. However, we do have to be careful because r and h are both variables. So when I take the derivative of them, if they're being multiplied, what do I have to do?
Chain rule?
Not
Or
the chain rule.
Product rule.
Multiplication or product rule. Yeah. So on the left hand side, the derivative of v is just what?
1.
1. However, I'm taking the derivative with respect to time, so I also have to multiply by a dv dt. Which is also important because that's what we're looking for. So if I didn't have that somewhere, then I wouldn't have anything to solve for. Now, is my 1/3 pi a variable?
No, it's constant.
Correct. So we do not need to do like a triple product rule, right? It's just a constant. So we can go ahead and just include the 1/3 pi along with our r squared. So remember that for our product rule, how do we start it?
F prime times G.
Yeah, so I'm going to take the derivative of the first part. So it's the derivative of r squared.
2R.
Okay, so I'm going to multiply that by my 1/3 pi. But again, what are we taking the derivative with respect to? Time. Yes. So what do we have to multiply by? dr/dt. And then we leave our g for our second function alone. So in this case, it's h. Okay. Then what operation goes in between?
Multiplication. Or addition.
Addition. And there we leave the first one alone and multiply by the derivative of the second one. So what's the derivative of h? 1. But again, I'm taking the derivative with respect to time, so I have to multiply by a dh. So that would be my answer. What questions do you have there? First, how we set it up? How we take our derivative?
Can we just plug it in for the DRDT or is that what we're doing next?
That's what we're doing next. I just want to make sure, because again, the setup part is really the hardest part. Because once I have the equation, the derivative is fairly straightforward. Sometimes we have to use a product rule like this, okay? But most of the time we're just using like a power rule or a basic product rule. So then yes, after that we can plug stuff in. But I just wanted to make sure that we all know kind of how we got up until this point. Because then yeah, if you notice on the right hand side, I have all of that stuff. We have r, we have h, we have dr/dt, and we have dh/dc. So then we can just type dr/dt is r -0.1. about solving, because basically what we are wanting to find is already solved for, yes?
Mhm.
Are all of those things numbers on the right hand side?
Yes.
Yes. So is the right hand side a numerical value?
Yes.
Yes. So if this was a free response question, is that a valid answer? Yeah. If all I have to do on the right hand side from here, if I can type everything on what I have left into a calculator and it would just give me a number, that is a numerical value, which means that we can stop. Okay? Because again, some of y'all, especially if this was a non-calculator active question, are not great with fractions and decimals. So we stop while we're ahead. Because you would get full credit for that question right there. However, if you decided to go forward and simplify it and then made a mistake, you would not get the point for your final answer because you're now saying that whatever you got is your answer instead. Now, if it was a calculator active question, or especially like if it was a multiple choice question, they are going to reduce it. So if we reduce that down, you are going to get negative pi over 5. Okay, and then also the last thing that we have to consider with our related rates is that all of these, most of them, are going to be word problems or contextual problems, which means that we want to talk about what our unit is. Okay, so what is the unit that we are using here?
Feet per minute.
Close. There are feet and there are minutes. What are we taking the rate of?
Volume.
Okay, and volume is a what type of unit? Cubic unit, yeah? So what do we need to have here then?
Cubic feet per minute.
There you go. Feet cubed per minute. Which makes sense because notice that my R is going to be in feet, my H is going to be in feet, and dr dt is in feet per minute. So I'm going to get feet cubed. Same thing here. R is in feet and I'm squaring it, and then dh dt is going to be in feet per minute. So I have feet squared times feet, which gives me cubic feet again. So. What questions do we have there? So why is our dv dt negative?
Because it's
Because it's leaking out, so my volume will be
Negative. Or not volume.
volume will be
Decreasing.
negative, but it'll be decreasing. So if my volume is decreasing, then its derivative should be negative. You ready for this one? This one should look vaguely familiar.
Might be fun. Reading this walking.
Find you.
No. I haven't gotten one yet. I need to just look one.
So it says air is being pumped into a spherical balloon at a rate of 4.5 feet cubed per minute. Find the rate of change of the radius when the radius is 2 feet. So, what do we want to do first? Draw a pretty picture. Which is helpful because remember we did look at something like this yesterday. Okay. What do we want to do next? What do we need next?
An equation.
An equation, okay, but what do we say we kind of have to know in order to be able to write the equation? Like, what variables am I going to use for our equation?
Volume.
Yeah, so we need to look at what we're given and what we need to find, yes? Because those are the things that I have to relate to each other. So if I don't know what those are, then it's really hard to make an equation. Yeah, or else like pull something out in there. So it says air responds into a spherical balloon at a rate of 4.5 feet cubed per minute. What does that represent?
The rate change in volume.
Okay, how did we figure that out?
It says feet cubed.
Okay, so if something is in cubic units, then there's a good chance that it's going to be volume. Also, if we think through it, right, air is going to be filling up the entire balloon, so the balloon will be expanding, right? So the space on the inside is what is growing, and that is represented by volume. So then next up, what does it ask us to find?
Rate of change in radius.
So that's going to be dr dt. So that's what we're trying to find, and we specifically want that when r is 2. Am I plugging in my r equals 2 from the beginning? No, because r is changing. So what is something that's going to relate my volume of a sphere to its radius? Do we have an equation for that?
Volume of the sphere.
Is what?
E equals 4 pi r squared cubed.
I r cubed. Do I have volume and do I have a radius? Yeah, those are the things that I'm given and the things that I'm looking for. Okay. So what would our derivative be?
4.5.
I mean, yeah, we need to take the derivative of the equation first before we can start plugging stuff in there.
dv over dt.
Okay. Equals
2r. Or 3r squared.
okay, so we need to multiply that by 4/3 pi. Do I agree derivative of r cubed is 3r squared, yes? So if I multiply 3 by 4/3, I'm just going to get 4 pi r squared. But again, what are we taking the derivative with respect to? Time. So we also have to multiply by a dr dt. So then, yes, I'm going to plug in a 4.5 for my dv dt. I have that my radius is 2. Now, for this one, okay, notice that I could not just straight plug all of that into my calculator as it stands. So that would not be a valid final answer. I do need to take this one step further, and we have to solve for whatever it is that we're looking for, which in this case is dr dt. Now, that would be a valid answer. Even though I haven't simplified it, we don't have to simplify it. Once I've solved for whatever it is that we're needing, that can be my final answer. But if we wanted to simplify a little bit, we can have 4.5 times, we would get 16 pi. And what would our unit be this time?
Feet per minute.
So notice that over here, right, this is going to be in feet squared, yes? And my volume was in feet cubed, yes? So I'm going to end up dividing feet cubed by feet squared, which just gives me feet. Or in other words, think that a radius is just a length. So I'm just going to have a foot. Yes, no, maybe. Now, usually on a lot of your AP free response questions, at least one of the points, so each AP question is kind of like my free response question, there's going to be like a part A, B, and C at least. Sometimes there's a D, okay? And one AP question is going to be worth 9 points. Usually somewhere in there, one of those points is going to be on your unit. Okay, so units are really easy to tack in on at the end. So make sure you're including correct units because it's a really easy point to get. Alright, what questions do we have on that one? Yes or maybe? Okay, we're stopping there for today.